A lot of other hard problems in math and science can be broken down and approximated as the sum of many small quantities. Things like figuring out how far a car has traveled based on its velocity at each point in time. In a case like that, you might range through many different points in time, and at each one multiply the velocity at that time times a tiny change in time, dt, which would give the corresponding little bit of distance traveled during that little time. I'll talk through the details of examples like this later in the series, but at a high level, many of these types of problems turn out to be equivalent to finding the area under some graph, in much the same way that our circle problem did. This happens whenever the quantities that you're adding up, the one whose sum approximates the original problem, can be thought of as the areas of many thin rectangles sitting side by side like this. If finer and finer approximations of the original problem correspond to thinner and thinner rings, then the original problem is going to be equivalent to finding the area under some graph. Again, this is an idea we'll see in more detail later in the series, so don't worry if it's not 100% clear right now. The point now is that you, as the mathematician having just solved a problem by reframing it as the area under a graph, might start thinking about how to find the areas under other graphs. I mean, we were lucky in the circle problem that the relevant area turned out to be a triangle, but imagine instead something like a parabola, the graph of x squared. What's the area underneath that curve, say between the values of x equals 0 and x equals 3? Well, it's hard to think about, right? And let me reframe that question in a slightly different way. We'll fix that left endpoint in place at 0 and let the right endpoint vary. Are you able to find a function, a of x, that gives you the area under this parabola between 0 and x? A function, a of x, like this, is called an integral of x squared. Calculus holds within it the tools to figure out what an integral like this is, but right now, it's just a mystery function to us. We know it gives the area under the graph of x squared between some fixed left point and some variable right point, but we don't know what it is. And again, the reason we care about this kind of question is not just for the sake of asking hard geometry questions. It's because many practical problems that can be approximated by adding up a large number of small things can be reframed as a question about an area under a certain graph. And I'll tell you right now that finding this area, this integral function, is genuinely hard. And whenever you come across a genuinely hard question in math, a good policy is to not try too hard to get at the answer directly, since usually you just end up banging your head against a wall. Instead, play around with the idea, with no particular goal in mind. Spend some time building up familiarity with the interplay between the function defining the graph, in this case x squared, and the function giving the area. In that playful spirit, if you're lucky, here's something that you might notice. When you slightly increase x by some tiny nudge, dx, look at the resulting change in area, represented with this sliver that I'm going to call dA, for a tiny difference in area. That sliver can be pretty well approximated with a rectangle, one whose height is x squared and whose width is dx. And the smaller the size of that nudge, dx, the more that sliver actually looks like a rectangle. Now this gives us an interesting way to think about how a of x is related to x squared. A change to the output of a, this little dA, is about equal to x squared, where x is whatever input you started at, times dx, the little nudge to the input that caused a to change. Or rearranged, dA divided by dx, the ratio of a tiny change in a to the tiny change in x that caused it, is approximately whatever x squared is at that point. And that's an approximation that should get better and better for smaller and smaller choices of dx. In other words, we don't know what a of x is. That remains a mystery. But we do know a property that this mystery function must have. When you look at two nearby points, for example 3 and 3.001, consider the change to the output of a between those 2 points, the difference between the mystery function evaluated at 3.001 and evaluated at 3. That change, divided by the difference in the input values, which in this case is 0.001, should be about equal to the value of x squared for the starting input, in this case 3 squared. And this relationship between tiny changes to the mystery function and the values of x squared itself is true at all inputs, not just 3. That doesn't immediately tell us how to find a of x, but it provides a very strong clue that we can work with. And there's nothing special about the graph x squared here. Any function, defined as the area under some graph, has this property, that dA divided by dx, a slight nudge to the output of A, divided by a slight nudge to the input that caused it, is about equal to the height of the graph at that point. Again, that's an approximation that gets better and better for smaller choices of dx. And here, we're stumbling into another big idea from calculus, derivatives. This ratio, dA divided by dx, is called the derivative of A. Or more technically, the derivative is whatever this ratio approaches as dx gets smaller and smaller. I'll dive much more deeply into the idea of a derivative in the next video, but loosely speaking, it's a measure of how sensitive a function is to small changes in its input. You'll see as the series goes on that there are many, many ways that you can visualize a derivative, depending on what function you're looking at and how you think about tiny nudges to its output. And we care about derivatives because they help us solve problems. And in our little exploration here, we already have a slight glimpse of one way that they're used. They are the key to solving integral questions, problems that require finding the area under a curve. Once you gain enough familiarity with computing derivatives, you'll be able to look at a situation like this one, where you don't know what a function is, but you do know that its derivative should be x squared, and from that, reverse engineer what the function must be. And this back and forth between integrals and derivatives, where the derivative of a function for the area under a graph gives you back the function defining the graph itself, is called the fundamental theorem of calculus. It ties together the two big ideas of integrals and derivatives, and it shows how, in some sense, each one is an inverse of the other.
Okay, so that's a bit more of that same video that I played earlier. And as I say, I will give you a link to all of the videos if you want to watch them. But I think the key thing that he's telling you is that by cutting things into smaller and smaller pieces, you can get a good approximation to whatever the problem is. But the other thing that he showed you in the first video is he was looking for the area of a circle. I mean, we've got an equation for that, which is pi r squared, obviously. But if you were trying to find the area of some kind of function that's to do with some project that you're working on in the future, the bottom line is you don't have to use integration. You could plot it out and then measure the area. You could break it down into rectangles or triangles or something. You can get a sort of a ballpark figure by doing something fairly coarse, can I say, fairly, pretty obvious. You're just trying to find an area. So is it bigger than this or is it smaller than that? You can get a region for it without having to do all of the heavy calculus stuff that we're doing at the moment. Okay, so the final thing that I want to do today is a bit of practical applications. So imagine we've got a cone like so. This is x, this is y, this is r, which is the size of the cone, this is h, which is the height of the cone. And I'm interested, let's do it in blue. I'm interested in the volume of water that's in there. So what I'm going to do is I'm going to take a skinny little bit of water and find the volume of that. So the volume of that skinny bit of water is equal to, this is x here and this is y here. Okay, so the volume of that skinny bit of water is the area, which is pi x squared, times the slight bit of change in y, which is dy. Okay, let's be clear what I'm saying. I'm saying that the volume of that little slice of water is given by that equation. So it's pi x squared, which is the area, times the height of it, which is dy. The volume of the whole thing, so this is v, let's call it y. So the total volume is equal to pi x squared dy integrated from 0 to h. Yes, that's right. How does x vary with respect to y? Well, by similar triangles we know that x over y, so x over y is equal to r over h. All right, so x is equal to ry over h, so x squared is obviously r squared y squared over h squared. So now the volume becomes v is equal to the integral from 0 to h of pi r squared y squared over h squared dy. All right. Now I'm going to integrate that, and that's going to give me pi r squared over h squared. They're all constants. Outside y cubed over 3. And that's going to be from 0 to h. You see I've got a y squared there, and so I raise the power by 1, so I get y cubed, and then I divide by the new power. Okay, and that's what we've been doing all along. So now I'm going to put the value of h in there, so that's going to equal pi r squared over h squared times, and this is now going to be h cubed over 3. Alright, so when I expand that, the h cubed and the h squared will cancel, so I'm going to get pi r squared h over 3, which is the volume of a cone. Okay, that is the equation of the volume of a cone, and that's where it's come from. So let's just review how we got there. So what we said is that the volume of a tiny slice of water there is pi x squared dy. Pi x squared is the area, and obviously the area changes as you go up or down the column there. And dy is the thickness of one of these little slices of water. Okay, so we're going to integrate that tiny volume from 0 to h, which is the total height of the cone. So we're integrating with respect to y, but we've got this h squared term. So what we've got to say is, okay, x over y is equal to r over h by similar triangles. So x over y is equal to r over h. Okay, and those are the similar triangles, which means that I can replace x with ry over h, put that into the equation. We've now got y squared instead of x squared, and obviously I can integrate y squared with respect to y. That becomes y cubed over 3, and out of the end of that we get the equation for the volume of a cone. Okay, now let's extend that a little bit. What happens if we want to find the volume of a sphere? So what we're going to do is we're going to have a sphere. That's not very spherical, is it? So we'll draw our axes, and this is a 3D shape. So this is y, this is x, and this is z. Okay, and what I'm interested in is, let's take a little slice as before. So the area of this is x and this is y. So the area of that little slice is equal to pi x squared. Okay, so the volume of that little slice is pi x squared dy. So the total volume, I'll call that v, is equal to the integral of pi x squared dy from minus r to plus r, because here's minus r down here and here's plus r up at the top there, and I need to integrate from the very bottom to the very top. Okay, so I've got a problem as before, that I've got x, I want to integrate x squared dy, so I need to replace x with some function of y. So let's just imagine the radius. So what we can say about that is that x squared plus y squared is equal to r squared, can't we? That's just Pythagoras. Okay, and it's x squared that I'm interested in, so I can say that x squared is equal to r squared minus y squared. Okay, so now I'm going to put that into my equation here. So I've got v is equal to, I'll take the pi outside because it's a constant. So instead of x squared, I'm going to get r squared minus y squared dy. All right, so I can integrate that. Let's just lift that up a bit. So that's and that's going from minus r to plus r, remember. So that's going to equal pi, and then I'm going to get r squared y, because that's a constant, minus y cubed over 3. Okay, minus r and r. Okay, so let's now put the upper value in. So that's going to equal pi outside. So I'm going to get r squared times r, so that's going to be r cubed minus r cubed over 3. Let's have another bracket there. And then it's going to be minus, now I'm going to put minus r in here, so that's going to be r squared times minus r, so that's going to be minus r cubed. And then this minus r is going to go in here, so that's going to give me, when I put r into that, I'm going to get minus r cubed, but I've already got a minus sign, so it's going to be plus r cubed over 3, isn't it? Okay, and then square brackets around that. Gotta watch your signs. So what I'm going to do is I'm going to multiply through by, I'm going to take a 3 outside, so I'm going to get pi over 3 outside of, then it's going to be 3r cubed minus r cubed minus brackets, I'll keep the brackets for now, then I'm going to get minus 3r cubed plus r cubed, brackets. Yeah, let's do this bit by bit. I'm just going to expand that bracket. So I'm going to get 3r cubed minus r cubed, so that's going to be 2r cubed minus, let's keep the bracket, so that's going to be minus 3r cubed plus r cubed, so that's going to be minus 2r cubed, brackets, so I need square brackets around that, pi over 3. Let's just move that up a bit. So I've got 2r cubed minus 2r cubed, so that's going to be 4, so that's going to equal pi over 3 times 4r cubed. Okay, so that equals 4 thirds pi r cubed, which I hope you already know is the equation of a sphere. Okay, which means that we've now derived both the volume of a cone and the volume of a sphere from first principles. So for the cone, we started with a little slice of water there, and we integrated for all the values of r, which is from 0 to h, which gave us pi r squared h over 3. And for the cone, we took a little sort of a disk of water, which is pi x squared times dy, to find the volume of that tiny volume, and then we've integrated that from minus r to plus r. Okay, and that's given us 4 thirds pi r cubed, which is the volume of a cone. Okay, I think that's it for now. So everybody who's had enough can go, and anybody who's got any questions, in the usual way, stick around. Okay, thank you everybody, and I'll stop the recording.